In this video, we're going to talk about 9.1 sequences. This is the beginning of our third major topic in calculus. Our first big topic was limits and derivatives. Our second big topic was integration, which we just finished at the end of chapter 8. And our third big topic here is going to be sequences and series. We'll do a little bit at the end in the next chapter, chapter 10, with some other stuff that doesn't fit into there. That's going to be parametric and polar equations. It's kind of off on its own, but this is the last major topic that you would have in a calculus, a single variable calculus course, is the sequences and series portion, which we're going to start talking about here. So our objectives here are to write the terms of a sequence, 2, to determine whether a sequence converges or diverges, 3rd, to write a formula for the nth term of a sequence, and 4th, to use properties of monotonic sequences and bounded sequences. You may have talked about sequences a little bit in a pre-calculus course in high school or in college, depending on your curriculum. If you haven't, then this is a good place to start. We've been dealing with some sequences already and just haven't defined what a sequence is. So let's go ahead and define here that a sequence is a list of numbers which can be thought of as a function whose domain is the set of positive or non-negative integers, meaning that its domain is either going to be the natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, so on, or the whole numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. It's a well-ordered set, so there's clearly a first, second, third, fourth, fifth member in the set, and so on. It just depends whether you start counting at 0, indexing at 0, or indexing at 1, and there are advantages in certain sequences to indexing them at 0, and for other sequences to indexing them at 1. So we'll use subscript notation instead of function notation. So consider the sequence 1, 2, 3, 4. So subscript notation. We'll say that the nth term of the sequence is equal to n. So that means that at n equals 1, a1 equals 1. At n equals 2, a sub 2 is equal to 2, and so on. That if we wanted to come down here to n equals 5 and jump all the way down there, we could skip the ones in between and say a sub 5 equals 5, and a sub 5, this is the 5th term in the sequence. Right? If we have a bn, this is just another way to index this. Bn could be equal to n plus 1, where we start indexing at 0. B0 is equal to 1 at n equals 1. B1 is going to be equal to 2, and so on. So if I wanted to get down here to B something equals 5, I'd need 5. I'd need this to be 4. 4 plus 1 is 5. So at B equals 4, but I'd still have 5 terms. 1, 2, 3, 4. This would be the 5th term here. So both of these are the 5th term in the sequence. So if I was to look at this as a function, f of n, actually, let's think of f of x. Yeah, f of n equals n, for n is an element of the natural numbers here. The natural numbers, just so you remember what they are the set of 1, 2, 3, 4, so on. If I talk about the whole numbers are 0, 1, 2, 3, so on and so forth, like that. So if I try and find, this is going to be defined for n equals 1, 2, 3, 4, and so on, the way that I've defined it, or I want this first notation here. But if I try and find f of 1.5, for example, that does not exist because 1.5 is not an element of the natural numbers. But f of 1 would be 1, f of 5 would be 5, and so on. This is the function form of that first one where I indexed it with the natural numbers. So this is indexed with the natural numbers. This is indexed with the whole numbers here. We can refer to n as the index of the sequence in the terms of the sequence a sub 1, a sub 2, all the way out to a sub n. The term in the nth place is called the nth term of the sequence. This is assuming we index the sequence with the natural numbers. Natural numbers are counting numbers. We start counting at 1. So what is the 10th term of the sequence? 2, 4, 8, 16. Well, we're going to have to think about what the pattern is there. And I see that as powers of 2. So this looks like 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, dot, 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 2 to the n. So I want to find out that a n is going to be equal to 2 to the 10th is going to be 10, 24. If you go ahead and multiply that all out, 2 to the 10th power is 10, 24. Now that we know that, can we find a way to write that entire sequence out and not just use these ellipses like this? Sure. So we can use these set brackets like this to represent a sequence, and we put the nth term in there, 2 to the n, and just like we do when we're evaluating an integral and we put our limits on the outside, we're going to put our lower limit here starting at 1 and our upper limit going to infinity like that. So this is our starting index, and this is our goes on forever. For n greater than or equal to 1 is what that tells us. So if I wanted to re-index this starting at 0 instead to use the whole numbers, then I would have to think about, well, this first term is 2 to the 0 plus 1, and that's 2 to the 1 plus 1, 2 to the 2 plus 1, 2 to the 3 plus 1, and so on, that this is 2 to the n plus 1 here as I go out. So this is 2 to the n plus 1 with n equals 0 to infinity here. And these two are equivalent sequences. They're just indexed differently, but the first one is indexed on the natural numbers and the second is indexed on the whole numbers. Sequences can be defined recursively by listing a few terms of the sequence. In some cases, we can define a formula for the terms of the sequence, and that's called a closed formula for the terms of the sequence. And we can get a formula like we've had up here where we can just stick in 10 and find what the 10th term is. That's a closed form. A recursive form, you have to go through all the previous terms to be able to get to the term that you wanted. So imagine that if I wanted to find the 10th term, I'd have to find the first, second, third, fourth, fifth, sixth, seventh, eighth, and ninth, and follow the pattern to be able to get to the 10th term. So in the above example here, we've recursively said 2, 4, 8, 16, and I can recursively see that each time I'm taking the previous value and multiplying by 2. So I could think of that as the last one is 2 times the previous term, like that. That's recursive. Whereas our closed form was, I recognized that that was 2 to the n, and I could stick in any value of n that I wanted to, or 2 to the n plus 1, and I could stick in any value that I wanted to in this formula that was closed. But if I only saw it as starting off with 2 and then multiplying by 2 and then multiplying by 2 and multiplying by 2, and I had to do that a whole bunch of times to get to the 10th term up here of 1024, that would have been quite the headache. So we could have done that here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We could have said this is 2, 4, 8, 16, 32, 64, 128, 256, 512, and then 1024. We could have done that, and that would have been a real pain. Imagine if this would have gotten even bigger than that, right? So let's try and see if we can write a closed form for the sequence here of 1, and then negative root 2, and then root 3, and then negative root 4, and then root 5, and then negative root 6. So I see a root n there going on, but I also see that the sign is changing, and it starts off with a positive sign. So I'm going to say maybe n plus 1, because it starts off with an even power on the negative 1 since it's positive, and then it goes to an odd power, and so on. So one of the ways that I can write this is, and you should know that negative 1 to the n goes from 1 to infinity, is going to be negative 1, 1, negative 1, 1, and so on. Whereas negative 1 to the n plus 1 from n equals 1 to infinity is going to be a positive 1, then a negative 1, then a positive 1, then a negative 1, and so on. So because this starts off with a positive term here, I'm going to be looking at negative 1 to the n plus 1 here, and that's why I chose that for my closed form here, n equals 1 to infinity. Let's see if we can write a closed form for the sequence here. Negative 2 over 1, positive 8 over 2, negative 26 over 6, 80 over 24, negative 242 over 120. So I recognize those numbers in the bottom to be something called factorials. 1 and then 1 times 2 is 2, 2 times 3 is 6, 6 times 4 is 24, 24 times 5 is 120. So n factorial is equal to n times n minus 1 times n minus 2 times ... times 1. So we're actually looking at it building from the other way here up to n. So I know that there's an n factorial in the bottom down here. And then this appears to be a power of 3 minus 1. So 3 to the n minus 1 is what that looks like. And then we have a sign changer that's negative 1 to the n is what that looks like to me. So that goes n equals 1 to infinity. So you're going to need to be able to recognize things like exponential functions. You're going to need to be able to recognize factorials. You're going to need to be able to even and odd things. We'll talk about some other things that you need to be able to recognize. Power functions like the sequence of all of the perfect squares, the sequence of all of the perfect cubes, so on. So we just looked at the factorial function. The factorial function denoted n factorial. The exclamation point is factorial is the product of all positive integers less than or equal to n. N factorial is n times n minus 1 times n minus 2 times n minus 3. So for example, 4 factorial is 4 times 3 times 2 times 1 would be 24. 3 factorial is 3 times 2 times 1 is 6. 4 factorial is 4 times 3 times 2 times 1, or 4 times 3 factorial. 4 times 6 is 24. So 5 factorial is going to be 5 times 4 factorial is 5 times 24 is 120, and so on. 6 factorial, this is usually about where you stop, is 6 times 120 is 720. We usually don't get above that. It grows very fast. So this is our newest, fastest growing function that we know about. N factorial grows faster than e to the x, e to the n here, since we're using n as our variable. And it really doesn't even matter what our base is. Any constant base there raised to the n power, n factorial is going to eventually overtake it. So when we take the limit of a sequence, we've been doing this for a while, we're going to let L be a real number. The limit of the sequence a sub n is L, written as limit as n goes to infinity of a sub n equals L. And then this is a technical definition. We didn't do delta epsilon proofs earlier in calculus 1, but this is the delta epsilon definition. If for each epsilon greater than 0, there is an m greater than 0, such the absolute value of a sub n minus L is less than epsilon whenever n is greater than m. If the limit of L of a sequence exists, then the sequence converges to L. If the limit L of a sequence does not exist, then the sequence diverges. This is the main piece that you need to know here is that we want to know about convergence or divergence of a sequence. So if this limit as n goes to infinity exists, the sequence converges to L. If the limit as n goes to infinity of the nth term does not exist because it oscillates or it goes to infinity or negative infinity or something like that, then the sequence diverges. So graphically speaking, we want the terms of the sequence to approach some horizontal asymptote, but they can be alternating on opposite sides is what this is saying. So if we've got L plus epsilon up here, and we've got L minus epsilon here, and we have L right here, then we want our terms to eventually at some point M stay bounded here between L plus epsilon and L minus epsilon. So let's say that they start off up here and then down here and then up here and then down here, and then up here, and then we start to get in here, and then maybe we're inside there and there, and they just keep bouncing back and forth, but getting closer and closer to this line, like this. Then after this 1, 2, 3, 4, 5, 6, 7th term right here, that there is a capital M here, is 7. So after the 7th term, I can say that they're always going to stay within this this boundary of plus or minus epsilon, which is really small. It's an infinitesimal from L. So we can find M. That was the question. Yes, M needs to be greater than 7 for this statement to be true. And then we're going to be going towards y equals L. That limit will exist. I know that we didn't actually do a whole lot of that with limits in our calculus 1. We didn't get into this rigorous definition here with delta epsilon, but some of the supplemental examples that I'm going to do from another textbook for that, I think I'm going to do some of the delta epsilon stuff there just to show you as an additional topic. So let's go ahead and look at the limit of a sequence here. Let L be a real number and F be a function of a real variable such that the limit as x goes to infinity of f of x equals L. Then if a sub n is a sequence such that f of n equals a sub n for every positive integer n, then the limit as n goes to infinity of a sub n should also equal L. So we can just think of this function here, a sub n, think of it like we used to do with x's, and whatever the limit was when we dealt with it with x's, and all those techniques that we did back with just regular old variables that could be any real number here, we can do those for sequences as well. So finding the limit of the sequence for 1 over n defined for n equals 1 to infinity, we're going to think of that as the limit as x goes to infinity of 1 over x, which equals to 0, which means that the limit as n goes to infinity of 1 over n is equal to 0. And that means that this sequence 1 over n equals 1 to infinity, converges to 0, but it converges, and it converges to 0. Properties of limits and sequences. So we know properties of limits here. So let limit as n goes to infinity of an be equal to L, and limit of bn as n goes to infinity be k. That is sequence A sub n converges to L, and sequence B sub n converges to k. Then if we take a scalar multiple C of the terms of A sub n and want to find the limit as n goes to infinity of that, that will be that scalar multiple C times L. C can be any real number, and C, the sequence C, A sub n, converges to C times L then. If we have a sum or difference, the limit as n goes to infinity of an plus or minus bn is equal to L plus or minus k, and the sequence an plus bn is going to converge to L plus k, and the sequence an minus bn is going to converge to L minus k. We have a product. The limit as n goes to infinity of an times bn is going to be equal to L times k, and the sequence an times bn converges to L times k. And we have a quotient rule here for limit as n goes to infinity of an divided by bn is equal to L over k, provided that b sub n is not equal to 0, and that k is not equal to 0. So if that's true, then the sequence an over bn converges to L over k under the same conditions here, that bn is not 0 and k is not 0, that bn doesn't converge to 0. So let's talk about convergence and divergence of sequences, and determine if the following sequences converge or diverge, and if they converge, state the value to which they converge. So let's go ahead and talk about how we did this in the past. Limit as n goes to infinity of 3 minus 4 over n plus 8 over n cubed. We did this in chapter 4 when we were doing Riemann sums. We said anytime that we had an n to the power of something in the denominator here, that these terms were going to go to 0. And we were left with 3 plus 0 equals 3. So it converges. It converges because the limit is finite, right? It exists and is finite. So now let's think about the limit as n goes to infinity of n approaches infinity. So the limit does not exist because it increases without bound as n approaches infinity. So this diverges. You're not allowed to say that the limit equals infinity necessarily, unless your teacher tells you that that's okay. I can say that it approaches infinity, but this means that, and that's what you should write if your teacher tells you to write that. So now let's go ahead and think about what happens here. 3 plus negative 1 to the n goes from 1 to infinity. Well, I don't know what this negative 1 to the n is going to do. As I go out to infinity, it oscillates back and forth between -1 and 1. So this could be 3 plus 1 or 3 minus 1. And so we just don't know what's going on here. So the limit does not exist and the sequence diverges. There is no one answer for what happens out there at infinity. Now let's look at this one. Degree of the top and degree of the bottom are the same. So we can use L'Hopital's rule, or we can go back to this idea up here from earlier on in calculus, and I like that one better because it just gets us to the answer faster. So we're going to say that this is the same thing as the limit as x goes to infinity of x squared plus 1 over 2x squared minus x plus 1. And I'm going to multiply by 1 over x squared, 1 over x squared for both of those. And that's going to give me limit as x goes to infinity of 1 plus 1 over x squared over 2 minus 1 over x plus 1 over x squared. That's going to be equal to 1 plus 0 over 2 minus 0 plus 0 is 1/2. If you wanted to use L'Hopital's rule instead, go right ahead. We'll get to the same place. I'll do that over here. Limit as x goes to infinity. If we did this, this would give me infinity over infinity as my indeterminate form. And I'd apply L'Hopital's rules. This is going to be 2x over 4x minus 1, which again goes to infinity over infinity as my indeterminate form. And I'd apply L'Hopital's rule again. 2 over 4 is equal to 1/2, and we get to the same answer here. So the sequence converges to 1/2. Let's talk about what a monotonic sequence is now. Monotonic will be a sequence. A sub n is monotonic when its terms are non-decreasing or when its terms are non-increasing. So it's monotonically non-decreasing when a sub 1 is less than or equal to a sub 2 is less than or equal to a sub 3 is less than or equal to a sub n is less than or equal to a sub n plus 1, and so on and so forth. It's monotonically non-increasing. A sub 1 is greater than or equal to a sub 2 is greater than or equal to a sub 3 is greater than or equal to ... It's greater than or equal to a sub n. Lots of times we want to talk about something that's just strictly monotonically increasing. If we say it's monotonically increasing, we won't have the equal to's here. We'll say A1 is less than A2 is less than A3, ... AN, and so on. If we say it's monotonically decreasing, then A1 is greater than A2 is greater than A3 is greater than ... greater than AN greater than ... It's like that. So one of the ways to figure this out is going to be with derivatives and to see if the derivative is always positive or always negative. If we're dealing with this, the derivative is allowed to be 0, where the terms are going to, where consecutive terms are going to be equal to one another, and so on. So let's determine whether the sequence is monotonic and determine whether each sequence having the given nth term is monotonic. So let's look at the terms here. A1 is going to be equal to 3 minus 1 is 2. A2 is going to be equal to 3 plus 1 is 4. A3 is equal to 3 minus 1 is 2. And you see it's increasing, then decreasing, then increasing, then decreasing, and so on. So this is 2, 4, 2, 4, dot, 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 dot. So this is not monotonic. All right. Now, if we look at this next one here, we can say B1 is going to be 2 over 1. 1 plus 1 is 2 over 2 is 1. B2 is equal to 2 times 2 over 1 plus 2 is 4 over 3. That's a little bit bigger. And then B3 equals 2 times 3 over 1 plus 3 is 6 over 4, which is 3 halves, which is a little bit bigger still. So now we want to know is B sub n plus 1 always bigger than B sub n in general? Let's figure out. So B sub n is equal to 2n over 1 plus n. B sub n plus 1 is equal to 2 times n plus 1 over 1 plus n plus 1. And I want to know 2n over 1 plus n less than or equal to 2 times n plus 1 over 1 plus n plus 1. That's my question here. If true, the sequence is monotonic. So because all these numbers should be positive here, because n is at least 1, I should be able to cross multiply here without losing the inequality sign. So 2n times n plus 2. Is it true that that's less than or equal to 2n plus 2 times 1 plus n? Let's see. So this is going to be 2n squared plus 4n. Is that less than or equal to 2n plus 2n squared plus 2 plus 2n? So this is going to be, simplify here, 2n squared plus 4n. Is that less than or equal to 2n squared plus 2n plus 2n is 4n plus 2? Absolutely. Do you see that? That this is the same here for both of them, and I'm adding 2 on the right. So absolutely this inequality sign is preserved. This is the same thing as saying 0 is less than 2 for all n that are in the natural numbers. Therefore, this sequence is monotonic. The only reason we wanted to find a few terms first here is to see that it looked like it was monotonically increasing. So we knew which way to make this sign here, that this n plus 1th term we thought was going to be greater than or equal to the previous term. If we saw these terms were decreasing, we would have flipped the sign around the other way and said that a sub n would be greater than or equal to a sub n plus 1. So that's why we found a few terms there first. Now let's talk about what it means to have a bounded sequence. We're about to get a theorem that talks about a monotonic bounded sequence. So we have to define monotonic, and we need to talk about what bounded is. So a sequence a sub n is bounded above when there is a real number m, such that a sub n is less than or equal to m. Think of big M as a maximum, right? For all n, the number capital M is called an upper bound of the sequence, and the sequence A sub n is bounded below if there's a real number. I don't like n. I like little m for minimum, less than or equal to an for all n. The number little m is called a lower bound of the sequence. Okay, so capital M is big. That's going to be an upper bound. It's going to be a maximum that the sequence is going to stay below that number. And little m is a minimum. That's a lower bound of the sequence, and a sequence is bounded when it's both bounded above and below, that all of the terms can be stuck between these horizontal lines, y equals little m on the bottom and y equals big M on the top. And then we know that it's a bounded sequence. So there's the theorem that I was telling you was coming, a bounded monotonic sequence. So bounded monotonic sequences, if the sequence A sub n is bounded and monotonic, it has to converge. So determine the following, if the following sequences are bounded and or monotonic. So let's look at the graph here. Negative n squared is going to be 0, 0, 1, -1, 2, -4, and so on and so forth. If we let f of x be equal to a negative x squared, we're going to get these points. And this is just this right-hand side of this parabola. It's not bounded below because as x goes to infinity, f of x goes to negative infinity. So this is why I was using all that phraseology up there when the limit did not exist, that I was saying it was increasing with that bound or decreasing with that bound or whatever. So I can say that this is monotonic here, that the terms are always going down. The a sub n plus 1 is always less than or equal to a sub n, or I can say a sub n is greater than or equal to a sub n plus 1. That's true. If I wanted to prove that, I would have to actually come here and say, set up my inequality and ask if negative n squared is always greater than or equal to negative n plus 1 squared. Yeah, negative n squared is greater than or equal to a negative n squared plus 2n plus 1. Negative n squared is greater than or equal to a negative n squared minus 2n minus 1. I'm going to need to do some algebra here and say 0 is greater than or equal to negative 2n plus 1. And then 2n greater than or equal to 1, n greater than or equal to 1/2. Sorry, greater than or equal to 1/2. Yeah, so we'll come back to that. So negative. This is a negative. This is a minus. And that is negative, and that's negative. All right, well, n is a natural number. It's always going to be greater than negative 1/2 because our starting point is 0. So yes, that's true for all n that are in the natural numbers. Watch out for sign errors like I almost made right there, right? But it's not bounded. So yes, it's monotonic, but not bounded. All right, second one here. We've got -1 to the n from n equals 1 to infinity. So we have -1. Then we have 1. Then we have, so this is, sorry, n equals 1 is -1, then 1, then -1, then 1, and so on. So we have an m and an m here that technically it's bounded, but it's not monotonic. So bounded, but not monotonic, because we're jumping back and forth, negative, positive, negative, positive. So we need to be both bounded and monotonic to ensure that we have a convergent sequence here. So let's look at 2 over n squared. That's going to be something that looks like this, because we're only dealing with the right-hand side here, where we're dealing with natural numbers. So we need to be greater than or equal to 5 here, actually. So at 5, we have 5, 2 over 25 there. And we're interested in, from there on out, we can prove that it's decreasing, that it's always decreasing, and that it's bounded below by this horizontal asymptote y equals 0. Let's prove that. So the limit as n goes to infinity, actually change this to x because our graph there is an f of x, of 2 over x squared equals 0. And now we need to see if it looks like it's monotonically decreasing. A sub n plus 1 less than or equal to a sub n for all n. That would be 2 over n plus 1 squared needs to be less than or equal to 2 over n squared. Is this true? Let's cross multiply and see. 2n squared, is that less than or equal to 2 times n plus 1 squared? 2n squared, is that less than or equal to 2 times n squared plus 2n plus 1? 2n squared, is that less than or equal to 2n squared plus 4n plus 2? Yeah, 0 is going to be less than or equal to 4n plus 2. If you have any question about that, let's go ahead and say that means that -2 is less than or equal to 4n, and -1/2 is less than or equal to n, which means n is greater than or equal to -1/2, which is absolutely true for all natural numbers, starting with 1. This is true for all n that are in the natural numbers. So yes, the sequence is monotonic and bounded, therefore it converges. Right? That's it. If we actually wanted to find what it converged to, then we've already done that here. There's the limit. It's converging towards 0. All right. That's it for this video. We'll come back next time and talk about 9.2 with series and convergence. We'll start to talk about partial sums there and apply this idea of a sequence to those partial sums to say if the sequence of the partial sums converges, the series is going to converge. That's our big definition that always works for convergence. We're just not going to want to always do things that way. So we're going to try and learn some other techniques in chapter 9 to talk about convergence of special types of series. The big idea for series is that if the sequence of the partial sums converges, the series is going to converge. See you next time for 9.2.